Well, good morning. This should be Thursday, and obviously I haven't been able to grade your exams, and I won't be able to until after I get back. But we need to get started with Module 11, which is on the subject of solutions and the chemistry of solutions. So initially there are three basic terms that you need to have an understanding of. They're fairly basic. A solution has both a solute and a solvent. So the solute is something solid that is dissolved into the solvent, and once that happens you have a solution. So once again, the solute is usually a powder or a solid which dissolves into a solvent, and once you've done that, then you have a solution. And he gives you a quick chemistry example there. Carbon dioxide and water yields basically carbonic acid in the water, so carbonate. And in order for something to dissolve in water, and I'm fairly certain I've gone over this some in class before, and he talks initially on page 352, which is the start of this module, about sodium chloride, and he reviews the ionic substance of sodium ion and the chloride ion, and he makes the strong point that it's the electrical attraction between these two, or the electronic attraction between the positive sodium and the negative chloride, which keeps them together. And if you turn the page on to 353, he provides you a nice little figure and diagram of what the solid of sodium chloride looks like. And it's a very block type of structure, and the smaller sodium ions are interspersed evenly within the larger chloride ions. And that's what salt looks like on the submicroscopic level. Next, in figure 11.2, he shows you the polar covalent structure of water. And I know, again, we've talked about this, and water has it's polar, meaning that on one side of it it's slightly negative, and on the other side of it it's slightly positive. And we won't go into the reasoning for that. We've covered that in previous modules. But what happens when you dissolve sodium chloride into water is that the water molecules, because of that slight positive negative charge, is able to get in between the sodium and the chloride ions and essentially break them apart. So when we talk about something dissolving in water, that usually means it's an ionic compound, and the ions are literally being broken apart by the water. And if you put salt into water, essentially it starts to dissolve from the outside and in. So the parts of the sodium chloride that are on the outside of that little chunk of salt, they start getting mixed with the water. The water permeates and splits off the sodium ions and the chloride ions. And it shows you in a figure 11.3 of what it looks like for water to dissolve sodium chloride. And so what you're going to see there is, if you look at on the bottom right side of that figure, you'll see the big negative chloride, blue chloride ion, and it's surrounded by three water molecules. Now don't worry about whether that's the proper size and whether it's three molecules of water. Don't worry about that. But the point is, you see that it's the hydrogen side of the water molecule which has the positive charge, which is surrounding the chloride ion. And if you look at just a little bit off to the upper left from that, you'll see the smaller sodium ion is now surrounded by, again, three water molecules, but it's the oxygen side, if you will, of the water molecule that's now being attracted to the positive sodium chloride. So each sodium and chloride ion gets completely surrounded by water. And something which we'll go over the experiment, we won't have you do the experiment, but you should get the impression that for the most part, water can only dissolve so much sodium chloride. because there's only so many water molecules to go around to dissolve everything. And as you see, since they have to completely surround it, once you've in a sense run out of water molecules to completely surround both the sodium and the chloride ions, well, that's it. You can't dissolve any more sodium chloride in that particular solution. And we'll see later on that temperature has a lot to do with that. And essentially the higher the temperature of the solvent, in this case water, the more sodium chloride you can dissolve into it. And the way that works would be basically heating water. All the water molecules just become more agitated and they move around faster. And so they have more energy, which means they're able to get inside and around the sodium ions and the chloride ions much more effectively. And they can break apart more and dissolve more because of that more rapid motion, because of the greater heat. And so we'll talk through that experiment a little bit later. But he also makes the point here that there are also some ionic compounds which are insoluble in water, which means they don't dissolve in water. And the reason being is that because the electronic attraction of the sodium and the negative ions is so large that the water molecules can't possibly squeeze in and separate them out. So there are some ionic compounds that won't dissolve in water, and it simply has to do with the strength of the charge attraction between the positive and negative ions. Now, if you turn the page over to 356, 357, he goes into a little bit more discussion and talks about not an ionic compound, but a polar covalent molecule, which is phosphorus trihydride, or PH3, and that he shows you in figure 11.4. And basically, he's allowed it to be represented in the proper pyramidal form, so that you're able to see that here also there will be a slightly negative side of this molecule and a slightly positive side of this molecule. And so this kind of compound is also able to dissolve in water, only it doesn't dissolve like the ionic compound. There's a similar process that goes on, but not quite the same. So if you look at figure 11.5, he shows you the phosphorus trihydride after it's been dissolved in water. And what you're seeing is that the negative side of each water molecule, the blue oxygen, is being attracted to each of the three hydrogens of the phosphorus trihydride. And then with the phosphorus part, which has a slight negative charge, you see that the two positive hydrogen ion molecules of water are attracted to it. So you still get a surrounding of the pH3 with water molecules. The main difference being here is that the pH3 molecule does not break apart. It's a polar covalent molecule, so it's not ionic, so the ions are not separating here. The molecule stays together, but it's similar in that sense to water, which is because it has a slightly positive, slightly negative side, and the water is able to get in and surround that molecule in different ways and essentially neutralize those slightly positive and negative sides of the molecule. So that's a basic discussion, at least with either ionic or polar covalent molecules, as they are able to dissolve in water. Water is the primary solvent that's used throughout most of chemistry. It is the solvent that's present in our bodies, so all of the basic biomolecules that are used in our cells, in our bodies, are soluble in water because they have a distribution of positive and negative charges that allows water molecules to surround them and allow them to be dissolved in water. Of course, that's not entirely the case with all things. I mean, fats obviously do not dissolve well in water, but we have ways of storing those in a special way and utilizing them in cells that allows them to at least be utilized in that aqueous environment of the cell. Now, Turn to page 358. It gives you a small little table there, figure 11.1. And it just provides a summary of how solutes dissolve in liquid solvents. So he talks about three different kinds of solutes, both solid, liquid, and gas. So the three different states of matter. Now a solid solute will dissolve when the solvent molecules are attracted to the solute molecules so strongly that the solvent molecules can get between those solute molecules or ions and pull them farther apart from each other so they get completely surrounded by water. But with the solid, again, it has to be that the solvent molecules are strongly attracted to the solute molecules. When you're dissolving a liquid in a liquid, and he makes the point that when you use liquid soap or liquid dishwashing detergent or anything like that, you are dissolving one liquid in another. And so there has to be, again, an attraction of charges. And he goes on to say that in this case, the solvent molecules need only be attracted to the solute molecules a little bit because they're both liquid already. The solvent doesn't need to separate the solute molecules very much. The solvent merely needs to get between them. And so again, any kind of liquid to liquid is going to be an easier solution to make than solid to liquid. And for gas, the solvent molecules, it says, must be attracted to the solute molecules enough to pull the solute molecules closer to one another. Now think about it, that's completely different here now. So that if it's a gas that you're trying to dissolve in a solvent, the gas molecules have to be able to be pulled closer to each other in order for it to dissolve. So you can see that there's a slightly changing process involved going from solid to liquid to gas, whereas solid, there has to be a strong attraction to break up the solute ions or molecules. But when you get down to gas, it actually there has to be enough traction where the gas molecules are at the solvent. The solute molecules are going to be attracted to pull them closer to each other. And still, the solvent will surround those closer attractions between the gas molecules or the solute molecules. But so it operates a little bit differently, and there's a part of one of the experiments ahead that is actually able to demonstrate a little bit of that for you. Now he talks next about an important concept of solubility, and he provides a definition on the bottom of 358. It says the maximum amount of solute that can dissolve in a given amount of solvent. So the maximum amount of solute in a given amount of solvent. So when you start out with a certain volume of solvent, the solubility is what defines how much of the solute now you can actually dissolve in that much of the solvent, in that volume. Now, in the middle of the next page, 359, he puts in boldface type that the solubility of any solute depends both on the identity of the solute and the identity of the solvent. And you've already seen that a little bit when you try to dissolve the salt crystals in the vegetable oil. You saw that it doesn't happen. Well, there isn't any kind of attraction between the vegetable oil and the positive and negative charged ions of the salt. So there's no way for the vegetable oil to permeate and get in between the ions of the sodium chloride, so it didn't dissolve. So both the identity of the solvent and the solute matter in getting this done. Next, he introduces the concept of a saturated solution, and it basically refers back to solubility, because in this case, a saturated solution is a solution in which the maximum amount of solute has been dissolved. You can't get any more solute into it. So if you have a beaker or a test tube of water, and you pour some salt in it, you get that to dissolve, and you pour some more salt in it, that dissolves, you pour some more salt in it, and you stir, and you can't get it all to dissolve. Well, you've reached saturation. And for that particular solvent, and we'll see later, at that particular temperature, that's all you're going to be able to get to dissolve into that particular volume of that particular solute. So he goes on, he starts describing an experiment, and I even thought about, it's a little bit late, this is Wednesday evening, and I'm leaving tomorrow afternoon. The procrastinator in me got the best of me again. I probably could have demonstrated this experiment to some degree. I mean, it's kind of limited here, and we're not exactly in front of a TV camera that gives a wide exposure, but I think I can walk you through this experiment. There's a reason why I'm not going to allow you to do this without me there, is because you need a flame and you need to heat things. So I would have preferred for me to actually be here to do this, but it's something you actually could do at home if you had all of the various ingredients here that he's talking about. So experiment 11.1 on 359 talks about the effective temperature on the solubility of solid solutes. It goes through the list of things you need, and what he tells you to do is to measure out 50 grams of table salt. That's not a lot, but it's actually quite a bit of salt. Actually, you're not going to put 50 grams of salt on your food. So he says put the salt into the 250 ml beaker or the glass that you have, and he warns you, if you do this at home and you're using a glass, you have to make sure it's fairly thick glass, or at least is not sensitive to heat. Some glasses that you might keep in your glass cabinet, if you actually put steaming hot water in some of them, they would just shatter and break. So you have to be careful if you don't have an actual beaker. So it says add 50 mils, about a quarter cup of water to the salt, and stir it vigorously with your stirring water or stirring rod, or however you can stir it. Allow the solution to stand a while. Now what's going to happen in this experiment is that all of that salt is not going to dissolve. You can stir and stir and stir, and you've got as much salt in there as you can get. Okay? And now he tells you to take out a piece of filter paper, and you arrange that, and you take out the funnel, and you pour this salt water through the funnel, because you want to eliminate the excess salt from the solution. So that's why you use the filter paper. The filter will remove the excess salt, and you now have a solution of saturated salt water, basically room temperature. Okay? So then he says to heat the solution, and as it's heating, stir the solution carefully with your thermometer. You will want to wear the oven mitt on the hand that's holding the thermometer. The thermometer will get hot, so you're going to have a thermometer, and you're heating this salt water, and you're stirring it using the thermometer to stir it with. And it says when the temperature reaches 95, and that's pretty close to boiling, so it's going to be really hot, and but it won't be boiling yet. Okay, so take the thermometer out of the solution, and use your hand that has the oven mitt on it to pick up the beakers. Obviously the beaker is that hot too. With your other hand, hold the funnel with the filter paper. Let me see. Okay, so you haven't really poured the water through the filter yet. So you got a little things that got ahead of myself here. You stir and stir and stir, and you see that there's still some salt left in the bottom of the solution. Then he tells you to heat that solution, but you've prepared your filter paper and funnel, and that's setting off to the side. And as the water is heating, you keep stirring, and you'll be able to see that more and more of that salt begins to dissolve in the solution, so it begins to disappear. Now, still, not all of it, even at 95 degrees, is going to dissolve. So then what you do is you carefully pour the solution onto the filter paper in the funnel. Make sure at this point it says the level of the solution doesn't rise above the filter paper. If that happens, if the filter paper is at this level and the water rises to this part, then what happens this high, then some of the water begins to slip down behind the filter paper, and you won't get a clean solution. Um, so you're pouring the solution through the funnel and through the filter paper. Continue to filter solution in this way until you have about 20 mils of the clear solution in the beaker that you had below the funnel. Okay. Now, it says look at your solution in the 100 mil beaker. That's the smaller one. It should be clear because all undissolved salt should have been filtered out by the filter paper. And this is a saturated solution of table salt, but it's saturated for 95 degrees Celsius. Now he says to place that solution in your freezer for about 20 minutes, which is all the more reason you need a good glass or an actual Pyrex beaker, because the difference between the heat and the freezer could crack and break most glass. So 20 minutes, and he said now after that remove the solution from the freezer and examine it again. So it's not that the water that you're putting in the freezer is going to freeze. 20 minutes is not that long a time, especially when it's almost boiling. But it will have cooled down some, and what you should see are crystals of salt lying on the bottom of the beaker. So what you did is you created a saturated solution at 95 degrees. But when you put the solution then back into the freezer and the solution begins to cool, then what begins to happen there is water can only hold so much salt as the temperature gets lower. It holds less salt than it did when it's 95 degrees. So what's going to happen there is that some of that salt is going to crystallize and essentially come out of solution. Just so you know, Baylor just came to visit me, and he's in here in the room with me, so he needs some attention every once in a while. So if I seem to bend over or my hands seem moving underneath what you're able to see, it's Baylor, and you just need some help, don't you, big boy? I don't know. We'll see. There he is. There's Baylor. He just comes and sees me every once in a while, don't you? Okay. All right. That was a good break. So, what's happening there is what's called the process of precipitation. And so he explains that right underneath the experiment on 360. Well, after filtering a solution, you had a saturated solution of table salt, but the solution was 95 degrees. When you placed the solution in the freezer, it cooled to a temperature of less than 0 degrees centigrade. Now, yeah, maybe it actually might get down that cool, that cold. He says, obviously the table salt is less soluble in cold water than in hot water because some of the table salt had to leave the solution and fall to the bottom of the beaker, the process by which a solute leaves a solution and turns back into its solid phase is called precipitation. And if you think about that, the word precipitation is something you associate probably with rainfall. Well, you have to understand that water technically in the upper atmosphere is in solution in the atmosphere. That's what clouds are. It's water vapor, it's water in solution in the atmosphere. And when that water falls as rain, it's precipitating out of solution in the atmosphere. And there's all sorts of different things that have to be in place for that to happen. So the meteorologist or the TV weatherman may be saying, well, we will have some moisture, but we won't get any precipitation, or a cold front will come through, but there won't be any rain because this, and this, and that. And so sometimes the atmospheric conditions aren't right to be able to precipitate water out of the atmosphere. So that shows you the effect of temperature. Now, what is interesting is that if that water actually got to 0 degrees, why didn't it freeze? Well, there still is some salt dissolved in the solution, and salt lowers the freezing point of water. So when you dissolve salt in the water, what happens is that you put it in the freezer, and depending upon how much salt you have in solution, it can even get below 0 degrees Celsius, and it still won't freeze. And that is the chemistry behind spreading salt on icy or snowbound roads. Used a lot more up north than it is here. Part of the problem with that is that the salt gets into the mechanism or the actual body work of the car, and back when cars used to be made actually out of metal, not so much anymore, but that would cause rust and deterioration of the car faster if you were up north because of the salt on the roads. They also use a little bit different salt that's not as corrosive anymore. So he introduces you then to another experiment on 361. He said this is the effective temperature on the solubility of a gas. Now he's going to use, as he describes it, soda pop for this experiment. And you can use 2 beakers or 2 saucepans. You need a test tube or tall thin glass will work. It must fit easily in the saucepans or in the beaker. And again, you need to be able to heat your solution. And you need a heater of some kind, and then or a stove, and then some ice, and of course the cold soda. So he says to fill one of the beakers or the pots about 3/4 of the way full with hot water. He says put it on the flame until the water begins to boil. So in this case, the reason he says use hot water because it's just already closer to boiling, it won't take as long. So you're going to boil some water in a pot or in a beaker, and basically also with the little flame heaters that come with the chemistry kits, it takes a really long time for that water to boil. So actually doing this experiment, these 2 experiments in the laboratory without some other kind of heating element just really doesn't work very well. So you put it on the flame, boil the water. While you're waiting for the water to boil, fill the other beaker half full with ice. That's why you need 2 beakers or you need 2 pots. One's going to get boiling water, the other one's going to get ice. Then add enough water so that the beaker is 3/4 full with an ice-water mixture. Now, you may wonder why you bother adding the water. When you add water to ice, some of the ice will then melt, but most of it will stay solid as ice, and there will be a slow melting of the ice into water. But what that does is it provides a fairly even temperature of 0 degrees Celsius or 32 degrees Fahrenheit. And with water, that's able to spread that cold a lot more evenly than if you just stick it into ice. With ice, you've got pockets of air, and the air itself will not cool the surrounding surfaces very fast at all. So when you use ice water, that cools things down a lot faster than just plain ice. So then he says, once the water starts boiling, extinguish the flames. The water's hot but not boiling. Number 5, fill the test tube 3/4 full with the soda. So with your small slumber gas or glass, you're going to put in a test tube about 3/4 full with soda. It needed to be cold to start with. So set the test tube in the beaker that contains the hot water and observe what happens. And again, you're going to have something that it's cold, and you put into something hot, it's not going to break. So observe what happens. Now what should start happening is you should begin to see bubbles coming up out of the soda. So it says in a few moments the soda should begin bubbling. Watch the soda bubble for a moment, then pull it out of the hot water. Place it in the beaker that contains the ice. So again, it's kind of Pyrex test tubes that we would have had in the chemistry kits work well. You can heat them almost to boiling, take them right up out of there and put them in the ice water, and they're not going to crack open, which would more and more usually be the case. So what happens? In a few moments, the soda stops bubbling. So you took the cold soda, you put it into hot water, and it begins to bubble. You take it out of there, you put it in the cold ice water, and the bubbling stops. So he says, again, go ahead and return the test tube to the hot water, and it should start bubbling again. You can do this a couple of times, but it doesn't last forever, and we'll explain that here in a minute. So part of his discussion here is he starts asking the question, well, is the soda boiling? Well, no, it's not. There's a lot of other things mixed into the water, and it would take a little bit more energy to bring it to boiling. What's actually happening is that what's dissolved in the soda is carbon dioxide. That's the carbonation for carbonated drinks. And it stays in solution in the water better at a cold temperature. You could observe this even if you simply just took a cold canned bottle of soda and just poured some in a glass and just left it on the counter. Over time, what you begin to see almost immediately is bubbles start rising to the surface, some right along the sides, some of it in the middle, but most along the sides where there's more warmth, and so it's getting heated up faster on the sides of the glass than on the inside. And if you leave an open can or bottle of soda or any carbonated beverage out long enough, eventually all the fizz is gone, all the carbonation is gone. Well, that's the carbon dioxide essentially coming out of solution at the warmer temperature, also at the lower pressure. To create carbonated beverages, you have to pressurize the carbon dioxide into solution as well. So that, I think we mentioned this in class once before, that when you pop the top of a can or a bottle, there's a rush of air. Well, the rush of air is going out of the can or bottle because the pressure was greater inside than it was outside. So you open that and there's and out comes the compressed air that was still in the can that was helping keep the carbon dioxide in solution. But also what's needed here is the temperature effect. So obviously that's why for most soft drinks, carbonated beverages, you serve them cold. You drink them cold because they maintain their carbonation longer, and that's what many people enjoy about a carbonated beverage. Not just the flavor, but the fizziness and the bubbles and the carbonation. There's a refreshing aspect to that. So keeping them cold maintains that carbonation much longer. So on the one hand, we saw that a higher temperature you can dissolve more solute in a solvent, and when you're and with temperature you can also vary how much of a solute comes out of solution, again based on temperature. We demonstrated that some even with the salt water, because when you cool down that boiling hot salt water, then some of the salt did indeed come out of solution, just like although it's the kind of the opposite effect here, that with the salt water you lower the temperature, some of the salt comes out of solution. However, with the gas dissolved in water, when you raise the temperature, more of the solute comes out of solution. So again, it depends on the identity of the solute and of the solvent. As a temperature, is it a gas into a liquid? Is it a solid into a liquid? And all those things matter in the chemistry of solutions. So on the top of 362, he kind of summarizes the two experiments. He says, for solid solutes, solubility usually increases with increasing temperatures. You can get more solid to dissolve at a higher temperature. The solubility of liquid solutes tends to not be affected at all by temperature. You want to be able to wash dishes or wash your hands with warm water, not because the soap dissolves better or worse at different temperatures, but the soap part of the liquid, that part of the solute, is more effective at a higher temperature. And you're breaking up the grease, or you're killing microorganisms, you're dissolving their cell membrane because of the soap, and that's what that does. Why that push recently, you saw some of the TV commercials probably where it says, I wash my hands with soap and water. Well, that's because you're busting open the membranes of any kind of cell that's on the outside of your skin, and most of those probably aren't good. So washing your hands with soap, with warm soapy water, is far more effective, sometimes even than the Purell hand sanitizers, because they kill, but they don't just break open and destroy. So soap and water is actually more effective. So if you've ever been on a cruise ship, yeah, when you go into a dining hall, they've got the Purell stands there, and you just grab some and get some on your hands. But they'll also make a point of telling you that you should also wash your hands soap and water, particularly after using the bathroom, and that helps curtail the spread of any kind of disease anyone on the ship might have. So soap and water, there's a reason, and temperature makes a difference there, not because the soap dissolves better in water at a higher temperature, but because the soap itself operates more efficiently at a higher temperature. And then he says the solubility of gases decreases with increasing temperature. So you increase the temperature of a gas solute in a solvent, and it will come out of solution. Whereas with solubility, you're able to put more of the solute into solution when you're dealing with a solid solute going into a liquid. Okay. And it kind of gives you another rule there in the middle of the page. It says increasing pressure increases the solubility of gases, and I hinted at that earlier with the discussion of the soda. Pressure does not affect the solubility of either liquids or solids. So with gases, that's the only time where pressure makes a difference. If you're going to get a gas to dissolve in a liquid, you're probably going to have to put it under pressure, and you'll get more of it in solution under higher pressure. Okay. So to close off today, we've got a few more minutes of what I'd like to take the time for, and on your own questions on the bottom 362. A student is asked to dissolve 50 grams of potassium chromate, an orange-yellow solid. So you'll need to determine, is that an ionic compound or not? Be thinking about that. In 250 mils of water. He's having a hard time getting all of the solid to dissolve, but is not allowed to add any more water. What should he try to do to make sure all 50 grams dissolve? Hopefully you're coming up with a fairly quick response to that. We just talked about on the upper part of the same page. Well, he can just increase the temperature. If he can't use more water, and he needs all of the potassium chromate to dissolve, it's an ionic compound. So it just needs to increase the temperature, and he'll get more and more of the solid to dissolve. Okay, 11.2, a chemistry lab is storing several bottles of a solution made by dissolving methane gas in octane, a non-polar liquid. Octane essentially is gasoline. So you'll see an octane rating on most of your gasolines at the pump, and that's what it's talking about. It's the amount of octane. So it's a 8 carbon chain molecule, and that's what octane is. And you want to dissolve methane, which is also non-polar gas. Okay. Laboratory chemist notices that every once in a while the lids from the bottles pop off. She reasons that the lids are popping off because the gas that is dissolved in the liquid is escaping from solution. What can she do to stop the lids from popping off? So think about that. Talk about it among yourselves if you want to. Just kind of discuss it. It's going to be the opposite of what you did in the previous question. So in this case, since it's a gas needing to be dissolved in a liquid, if you lower the temperature, you'll help keep the gas in solution in the liquid. So in this case, she needs to refrigerate or at least lower the temperature of these containers, and the lids will stop popping off. The gas will stay more contained and it will stay dissolved in the liquid. So 11.3, a student is doing an experiment that involves dissolving a gas in water. notices that even though the temperature in the lab is exactly the same every day of the year, there are some days in which more gas can dissolve in water as compared to other days. So the temperature is the same. Temperature is not changing. What most likely is changing from day to day in order to produce this effect? So take a couple minutes, just a few seconds really, probably all you really need. Discuss it among yourselves. What do you think? Temperature is the same. There's a gas dissolved in a liquid, and but there can be variation from day to day as to how much gas can be dissolved. If you go back up to the middle of the page, that second bold-faced line, pressure, the first line, increasing pressure increases the solubility of gases. Something that changes from day to day is the barometric pressure, or the amount of pressure that the atmosphere is exerting on the surface of the earth. What's called a low pressure is when the pressure gets less, and that usually brings a cold front. A high pressure is like what happens in Texas in the summer. High pressure settles over the state of Texas primarily, and it just sits there. And since it's high pressure, vapor can't rise, and you're not going to get any clouds, and you're not going to get any precipitation. So it stays hot and dry. So high pressure. So the pressure outside can change slightly, and depending on the gas and depending on the conditions he's using, primarily since you know it's water, it's the identity of the gas itself that might make a difference. Slight changes in barometric pressure in the atmosphere from day to day, which does happen, may alter how much of that gas you can dissolve in the liquid. Okay, so for next week, you're going to need to continue reading on ahead, and something that, well, I'll talk about it at the beginning of next session, and but try to read the rest of this module. There's about another 15, 16 pages to go, so get caught up. Thanks.